So here's something that might seem a little strange to think about right now. Lying there in the dark, maybe with a pillow pulled just right, the day finally winding down. Every single thing happening around you. The mattress pushing up against your body, the air filling your lungs, the faint hum of whatever's running in the background, the warmth slowly leaving your hands as you settle in. All of it, every bit of it, is governed by a handful of rules. Not thousands of rules, not millions. A handful. And those rules, the ones we call the laws of physics, they're the same ones keeping the moon in orbit right now, the same ones that make stars burn, the same ones that let your phone charge on the nightstand. The whole universe, from the smallest thing we've ever detected to the largest structure we've ever mapped, runs on this surprisingly short list of principles. And tonight, we're just going to walk through them. Slowly. No rush. We'll start at the very beginning. And I mean the very beginning. With the people who first looked at the world and thought, wait, maybe there are rules here. Maybe this isn't all chaos. Let's go back. Way, way back. Ancient Greece, around the 6th century BC. There's a guy named Thales, living in the city of Miletus, which sits on the coast of what's now Western Turkey. Thales is a merchant, a traveler, probably a bit eccentric, and he does something that, honestly, might be the most important intellectual move in all of human history. He asks a question that sounds almost childishly simple. What is everything made of? Not which god controls the rain, not what ritual will make the crops grow. Just, what's the basic stuff? What's underneath all of this? His answer was water. Everything is made of water. And look, that's wrong. We know that now. But here's the thing. The answer almost doesn't matter. What matters is the kind of question he was asking. He was saying, I think the world follows natural rules, and I think we can figure them out by thinking carefully and observing what happens. That's it. That's the seed of everything. Every physics textbook, every space mission, every bridge that holds your car, every circuit in every device you've ever touched. It all traces back to that impulse. The world isn't random. It has structure. And we can understand that structure. Now Thales wasn't alone. After him came a whole tradition of thinkers in the Greek world who kept pushing on this idea. Anaximander, Anaximenes, Heraclitus, names that sound like they belong in a fantasy novel. But these were real people, having real arguments about the nature of reality. Heraclitus said everything was fire. Anaximenes said air. They disagreed on the details, but they all shared that core conviction. There's an underlying order. And then, a couple of centuries later, you get Aristotle. And Aristotle is worth spending a minute on, because his ideas about physics dominated Western thinking for nearly 2,000 years. 2,000 years. Think about that. Whatever you believe about the world right now, imagine people still teaching it in the year 4025. That's the kind of staying power Aristotle had. Aristotle's physics was built on observation, which sounds great, except that he trusted his casual observations a little too much and didn't always test them rigorously. His basic picture went something like this. Everything in the earthly realm is made of 4 elements: earth, water, air, and fire. Each element has a natural place it wants to be. Earth wants to be at the bottom, fire wants to be at the top, and water and air sort themselves in between. When you drop a rock, it falls because it's made of earth, and earth's natural place is down. When a flame flickers upward, that's fire seeking its natural place above. Makes intuitive sense, right? You can see why people bought it. But here's where it gets tricky, and here's where Aristotle's physics starts to quietly go wrong in ways that would take centuries to untangle. He believed that heavier objects fall faster than lighter ones. If you drop a big rock and a small rock, the big one hits the ground first. And honestly, if you actually try this in everyday life, it kind of looks true, because air resistance messes things up. A feather falls slowly. A hammer falls fast. Aristotle looked at that and said, "Yep, heavier things fall faster. Case closed." He also believed that objects in motion need a continuous force to keep them moving. Push a cart, and it moves. Stop pushing, and it stops. That seems obvious, right? You push things to make them go, and when you stop pushing, they stop going. It matches your everyday experience perfectly. The problem is, it's wrong. Beautifully, subtly, importantly, wrong. And figuring out exactly how it's wrong would become one of the great intellectual achievements of the human species. But we'll get there. We'll definitely get there. For now, just sit with Aristotle's picture for a moment, because it's actually a lovely framework if you don't poke at it too hard. The universe has a center. That's the Earth. Everything has a natural place. Motion happens when things are trying to get to their natural place, or when something is forcing them away from it. The heavens above are made of a fifth element, a perfect, unchanging substance, and they move in perfect circles, because circles are the most perfect shape. It's elegant, it's tidy, and for a very long time, it was enough. But the universe doesn't care about elegance, and it definitely doesn't care about tidiness. And slowly, over centuries, cracks started to appear. Let's jump forward to the late 1500s. We're in Italy now, and there's a young man named Galileo Galilei who's about to cause an enormous amount of trouble. Galileo is one of those figures who's so famous that he's almost become a cartoon. The guy who dropped things off the Leaning Tower of Pisa. The guy who got in trouble with the church. But the real Galileo is so much more interesting than the cartoon version. He was born in 1564 in Pisa, the son of a musician. His father, Vincenzo Galilei, was actually a pretty serious music theorist who did experiments on strings and sound. And that matters, because Galileo grew up in a household where you questioned received wisdom and you tested things. Vincenzo had challenged the established musical theories of his day, and he'd done it by actually running experiments, stretching strings under different tensions, and measuring what happened. So when young Galileo started questioning Aristotle, he wasn't coming out of nowhere. He'd learned from his father that the old authorities could be wrong, and that the way to find out was to go look. Here's what Galileo did that was so revolutionary, and it's simpler than you might think. He slowed things down, literally. He realized that falling objects move too fast to study carefully. You drop something, and boom, it's on the ground. You barely saw what happened. So instead of dropping things, he rolled balls down inclined planes, a gentle slope. The ball accelerates, but slowly enough that you can actually measure what's happening. You can time it. You can compare. And what he found contradicted Aristotle directly. The distance a ball travels isn't proportional to the time it's been rolling. It's proportional to the square of the time. In other words, in the first second, the ball might roll 1 unit of distance. In 2 seconds, it's rolled 4 units. In 3 seconds, 9 units. The ball is speeding up, and it's speeding up in a very specific, mathematical way. Acceleration is constant. That's huge. That's the beginning of real quantitative physics. He also showed, and this is the part everyone remembers, that heavy objects and light objects fall at the same rate, as long as air resistance isn't a major factor. Now, whether he actually dropped things off the Leaning Tower of Pisa is debated. The story comes from a biography written by his student Vincenzo Viviani, and some historians think Viviani might have embellished a bit. But Galileo definitely did the experiments with inclined planes, and he definitely reached the right conclusion. Weight doesn't determine how fast something falls. Aristotle was wrong. But here's what's really clever about Galileo, and this is the part that doesn't get enough attention. He didn't just show that Aristotle was wrong about falling objects. He started developing a completely different way of thinking about motion itself. Remember Aristotle's idea that you need a continuous force to keep something moving? Galileo began to see that this was backward. He noticed that a ball rolling on a smooth, level surface will keep rolling for a very long time. The smoother the surface, the longer it rolls. And he made a brilliant mental leap. If you could somehow remove all friction, all resistance, the ball would roll forever. It wouldn't need a push to keep going. It would just keep going. This idea that an object in motion tends to stay in motion unless something stops it is so fundamental that we barely even think about it now. But in Galileo's time, it was radical. It completely inverted the Aristotelian picture. For Aristotle, rest was the natural state, and motion required explanation. For Galileo, motion was just as natural as rest. What required explanation wasn't why things move, but why they stop. And that shift in perspective, that simple inversion, is one of the most profound insights in the history of human thought. Now, Galileo didn't fully formalize this into a clean law. He got close, but he was still working things out, still tangled up in some older ideas. He thought, for instance, that the natural motion of objects without forces would be circular, following the curve of the Earth, rather than in a straight line. So he had the right instinct, but not quite the right formulation. The person who would take Galileo's insights and hammer them into precise universal laws was someone who was born in England on Christmas Day, 1642, the same year Galileo died. And that person, of course, was Isaac Newton. But before we get to Newton, let's just pause for a moment and appreciate something. Between Aristotle and Galileo, nearly 2,000 years passed. 2,000 years during which the smartest people in Europe, scholars, philosophers, monks, mathematicians, mostly accepted Aristotle's physics as basically correct. There were exceptions, sure. In the 14th century, scholars at the University of Paris, particularly Jean Buridan and Nicole Oresme, had started poking holes in Aristotle's theory of motion. Buridan developed something called impetus theory, which was a kind of halfway house between Aristotle and Galileo. The idea that when you throw a ball, you impart an impetus to it, an internal force that keeps it going, but gradually gets used up. It wasn't quite right, but it was getting closer. Oresme even developed early graphical methods for analyzing motion that anticipated some of what Galileo would later do. And in the Islamic world, scholars like Ibn al-Haytham, working in Cairo around the year 1000, had made extraordinary contributions to optics and the scientific method itself. Al-Haytham insisted on experimental verification in a way that was centuries ahead of European practice. His book on optics was eventually translated into Latin and influenced European thinkers enormously. So the story of physics isn't just a European story. It's a global one, with ideas flowing across cultures and centuries in ways that are sometimes hard to trace. But the point is, progress was slow, agonizingly slow by modern standards. And one of the reasons it was slow is that Aristotle's physics felt right. It matched everyday experience. Things do seem to need a push to keep moving. Heavy things do seem to fall faster than light things, at least in the messy, air-filled world we actually live in. The genius of Galileo wasn't just that he was smarter than everyone else. It was that he figured out how to strip away the messiness and see the clean, simple truth underneath. He figured out that the everyday world is actually a terrible laboratory, full of friction and air resistance and complexity, and that if you want to understand the real rules, you have to design careful experiments that minimize all that noise. That's a lesson that still matters, by the way. Every time a physicist builds a vacuum chamber, or cools something down to near absolute zero, or smashes particles together in a miles-long accelerator, they're doing the same thing Galileo did with his inclined planes. They're trying to strip away the mess and see the fundamental rules underneath. So now, we're at the doorstep of Newton. It's the second half of the 17th century, and the intellectual world is buzzing. Galileo has shown that Aristotle's physics is flawed. Kepler, working with Tycho Brahe's meticulous astronomical observations, has figured out that planets move in ellipses, not circles, and that they sweep out equal areas in equal times. Descartes has developed coordinate geometry, giving people a powerful new mathematical language. Huygens is working on pendulums and optics. Robert Hooke is experimenting with springs and elasticity. The pieces are all there, scattered across Europe, in the notebooks and letters of dozens of brilliant people. What's missing is someone to put them all together into a single, coherent framework. And that someone is about to arrive. Isaac Newton, born premature and so small, his mother said he could have fit inside a quart mug, raised by his grandmother after his mother remarried. A lonely and intense child who grew into a lonely and intense man. Newton is about to do something that no one had ever done before. Something so ambitious, it almost sounds absurd when you say it out loud. He's going to write down the rules that govern all motion, everywhere, for all time. The motion of a thrown ball and the motion of the moon. The fall of an apple and the orbit of a planet. All of it, unified in a handful of mathematical statements, so precise and so powerful that engineers would still be using them to land spacecraft 300 years later. But the story of how he got there, the years of obsessive work, the bitter rivalries, the strange personality of the man himself, that's a story worth telling properly. And it starts in a small village in Lincolnshire during a plague year, when the universities shut down and a young man went home with nothing to do but think. And what he thought about during those months would change the course of human understanding forever. In the summer of 1665, the Great Plague was sweeping through England. Cambridge University closed its doors, and Newton, then just 23 years old, retreated to Woolsthorpe Manor, his family's modest farmhouse in the countryside. And here's the thing about Newton during this period. He didn't have a lab. He didn't have colleagues to bounce ideas off. He didn't have the resources of a university. He had his own mind, some books, and an almost frightening capacity for sustained concentration. Later in life, when someone asked him how he'd made his discoveries, he reportedly said, "By thinking on them continually." And he wasn't exaggerating. Newton could hold a problem in his head for hours, days, weeks, turning it over and over, refusing to let go until it yielded. It's a quality that made him extraordinarily difficult to be around as a person, but almost supernaturally effective as a thinker. During those plague years, roughly 1665 to 1667, Newton made breakthroughs in 3 separate areas that would each, individually, have been enough to make someone the most important scientist of their generation. He developed the foundations of calculus, which he called his method of fluxions. He conducted his famous experiments with prisms, showing that white light is actually composed of a spectrum of colors, and he began formulating his theory of gravity and the laws of motion. All 3, in about 18 months, while sitting in a farmhouse during a pandemic. It's one of the most extraordinary bursts of intellectual productivity in recorded history, and honestly, it's a little hard to wrap your head around. Let's focus on the physics, because that's where the story gets really interesting for us. Newton's insight, the big one, the one that changed everything, was that the same force that makes an apple fall from a tree is the same force that keeps the moon in orbit around the Earth. Now that might sound obvious to you, because you grew up in a world where that idea is just part of the background knowledge everyone absorbs. But in the 17th century, this was a radical claim. Remember, for almost 2,000 years, people had followed Aristotle's division of the universe into 2 fundamentally different realms: the terrestrial, where things are messy and imperfect and fall down, and the celestial, where things move in perfect circles forever. The idea that earthly physics and heavenly physics were the same physics. That was a wall Newton was tearing down. And he didn't just assert it, he proved it mathematically. Here's how the reasoning goes, and it's worth walking through slowly because it's genuinely beautiful. Newton knew from Galileo's work that objects near the Earth's surface accelerate downward at a specific rate, about 32 feet per second squared, or roughly 9.8 meters per second squared if you prefer metric. An apple falls, and in each successive second, it's moving faster than it was the second before, by that same amount. That's gravity pulling on it. Now, Newton also knew from Kepler's work that the moon orbits the Earth in a roughly circular path, taking about 27 1/3 days to complete one orbit. And he knew the approximate distance to the moon, about 60 times the radius of the Earth. So he asked himself a question. If gravity is what's holding the moon in its orbit, and if gravity gets weaker with distance, does the math actually work out? Think about what the moon is doing. It's moving sideways, tangent to its orbit, but it's also constantly falling toward the Earth. It's just that it's moving sideways fast enough that the Earth's surface curves away beneath it at the same rate it falls. The moon is, in a very real sense, perpetually falling and perpetually missing. That's what an orbit is. It's not that there's no gravity in space. There absolutely is. It's that the object in orbit has exactly the right sideways velocity to keep falling around the curve of the Earth instead of into it. And this is one of those ideas that, once you really get it, changes how you see the night sky. Every satellite, every space station, the moon itself, they're all falling, continuously. They just never hit the ground. So Newton calculated how much the moon falls toward the Earth in 1 second. If you work out the geometry of a circular orbit, how far the moon deviates from a straight line path in 1 second, you get a tiny distance. And then he compared that to how far an apple falls in 1 second at the Earth's surface. The ratio between those 2 accelerations should, if gravity follows an inverse square law, be related to the square of the ratio of the distances. The moon is about 60 Earth radii away, so gravity there should be about 1/3600th as strong as it is at the surface. 60 squared is 3600. And when Newton did the calculation, it worked. Not perfectly at first. The early estimates of the Earth's radius weren't quite right, and that bugged him for years. But eventually, with better measurements, the numbers lined up beautifully. The same force, following the same mathematical rule, governed both the apple and the moon. Now, Newton didn't publish any of this right away. And this is where his personality becomes part of the story. Newton was secretive, suspicious, and pathologically afraid of criticism. He'd work out extraordinary results and then just sit on them. For years, sometimes decades. He didn't publish his work on calculus for ages, which later led to one of the most vicious priority disputes in the history of science, with Gottfried Wilhelm Leibniz, who developed calculus independently in Germany. That fight got ugly. Accusations of plagiarism, nationalistic rivalries between English and continental mathematicians, letters full of barely concealed contempt. Newton used his position as president of the Royal Society to essentially stack the committee investigating the dispute, which found in his favor. It was not his finest moment, but that's Newton, capable of the most sublime intellectual achievements and the pettiest personal vendettas, sometimes in the same week. The person who finally dragged Newton's physics into the light was Edmund Halley. Yes, the comet guy. In 1684, Halley visited Newton in Cambridge and asked him a question that had been stumping the best minds in London. If gravity follows an inverse square law, what shape would a planet's orbit be? Newton answered immediately, an ellipse. He'd worked it out years ago. Halley was stunned and asked to see the proof. Newton couldn't find his notes, promised to redo the calculation and send it along, and what he eventually sent was so extraordinary that Halley essentially became Newton's editor, cheerleader, and financial backer, personally funding the publication of what would become the Principia Mathematica, the mathematical principles of natural philosophy, published in 1687. And here's a fun detail. Halley paid for the printing partly because the Royal Society had blown its budget publishing a lavishly illustrated book about fish. So the most important scientific work in history almost didn't get published because of a book about fish. History is weird sometimes. The Principia is where Newton lays out his 3 laws of motion, and these are worth going through carefully because they're the foundation of everything that comes after. The first law, the law of inertia, says that an object at rest stays at rest, and an object in motion stays in motion in a straight line at constant speed, unless acted upon by a force. This is Galileo's insight, refined and stated precisely. And it's deeply counterintuitive if you live in a world full of friction and air resistance, which is why Aristotle got it wrong. In everyday life, things do seem to stop unless you keep pushing them. But Newton is saying that the stopping is caused by something, friction, air drag, whatever, and that in the absence of those forces, motion would continue forever. No force is needed to maintain motion. Force is needed to change motion. The second law is the famous one. Force equals mass times acceleration. F equals ma. It looks simple, just 3 letters and a multiplication sign. But think about what it's actually saying. It's saying that if you know the forces acting on an object and you know its mass, you can calculate exactly how its motion will change. Not approximately. Exactly. It's a recipe for prediction. You tell me the forces, I'll tell you the future. And this works for everything from a baseball to a bullet to a spacecraft. When NASA engineers plot a trajectory to Mars, they are using F equals ma. When a structural engineer calculates whether a beam will hold, they are using F equals ma. It is, in some sense, the most useful equation ever written. The third law. For every action, there is an equal and opposite reaction, is the one people quote most often, but probably understand least. It doesn't mean that if you push on a wall, the wall pushes back and everything cancels out and nothing happens. It means that forces always come in pairs, acting on different objects. When you push on a wall, the wall pushes back on you. When the Earth pulls on the moon with gravity, the moon pulls on the Earth with exactly the same force. When a rocket engine pushes exhaust gases downward, the exhaust gases push the rocket upward. The forces are equal in magnitude and opposite in direction, but they act on different things, which is why the rocket accelerates even though the forces are equal. This is subtle, and it trips people up, but once you see it clearly, it's elegant. Every force in the universe has a dance partner. And then, layered on top of these three laws, Newton gives us his law of universal gravitation. Every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Every object, not just planets and moons. You and the chair you're sitting in are gravitationally attracted to each other right now. The force is unimaginably tiny, so small you'd never notice it, but it's there. Gravity doesn't turn off. It doesn't have a maximum range. It reaches across the entire universe, getting weaker with distance, but never quite reaching zero. And the inverse square part, the fact that doubling the distance cuts the force to a quarter. That's not arbitrary. It falls out naturally from the geometry of three-dimensional space, from the way the surface area of a sphere grows as the square of its radius. There's something almost inevitable about it. With these tools, three laws of motion and the law of gravitation, Newton could explain an astonishing range of phenomena: the orbits of all the known planets, the motion of comets, the tides, which are caused by the differential gravitational pull of the moon on different parts of the Earth, the precession of the equinoxes, that slow wobble of the Earth's axis that takes 26,000 years to complete, the shape of the Earth itself, which Newton correctly predicted would be slightly flattened at the poles and bulging at the equator because of its rotation. He explained why things fall, why the planets move the way they do, why the tides rise and fall, all from the same handful of principles. It was a unification of knowledge that the world had never seen before, and in some ways has never seen since, at least not until Einstein. But here's what's really worth sitting with for a moment. Newton's laws aren't just descriptions of what happens. They're predictive. They let you calculate what will happen in situations that have never been observed before. And that predictive power is what makes them engineering tools, not just philosophical statements. You can use them to design things, to build things, to figure out in advance whether a bridge will hold, or a rocket will reach orbit, or a satellite will stay in its intended path. That's the leap from understanding nature to controlling it. And it's why Newton's work marks the real beginning of physics as we know it, as a discipline that doesn't just explain the world, but gives you the mathematical machinery to reshape it. The impact was enormous, but it wasn't instant. The Principia was written in Latin, dense with geometric proofs, and extraordinarily difficult to read. Even many of Newton's contemporaries struggled with it. On the continent, there was resistance, partly because Descartes had proposed his own theory of planetary motion involving vast swirling vortices of invisible matter, and many French and German philosophers preferred that picture to Newton's spooky action-at-a-distance gravity, which seemed to pull objects toward each other across empty space with no mechanism, no contact, no explanation of how. Newton himself was uncomfortable with this. He famously wrote, "I have not been able to discover the cause of those properties of gravity from phenomena, and I frame no hypotheses." He was saying, "I can tell you exactly how gravity behaves, mathematically, but I cannot tell you why it works or what it is. And that distinction between describing a law and explaining its mechanism is one that physics has wrestled with ever since. And honestly, it's one of the most profound ideas in all of science. So let's just stay here for a minute longer. Think about what Newton was really saying. He was saying that a law of physics can be extraordinarily precise, can predict outcomes to many decimal places, can govern the motion of every object in the universe, and still leave you completely in the dark about the deeper reason it works. The equation tells you what. It doesn't tell you why. And Newton had the intellectual honesty to say so. He could have made something up. He could have proposed some invisible fluid or ethereal substance that transmitted gravitational force, the way Descartes had with his vortices. But he didn't. He said, essentially, the math works, the predictions match reality, and I refuse to pretend I know more than I do. That restraint, that willingness to separate what you can demonstrate from what you can only speculate about. That's not just good science. That's a whole philosophy of knowledge. And it's one that would echo through centuries of physics to come. But the resistance on the continent was real, and it lasted decades. In France especially, the Cartesian picture, those swirling vortices carrying planets around the sun like leaves caught in a whirlpool, had a deep hold on the intellectual culture. It felt more intuitive, more mechanical. You could almost picture it. Newton's gravity, by contrast, was mathematically elegant but conceptually disturbing. How does the sun reach across 93 million miles of empty space and pull on the Earth? What's doing the pulling? There's nothing there. It bothered people. And honestly, it should bother you a little too, because it is strange. We've just gotten used to it. The person who probably did more than anyone to bring Newtonian physics to the continent was a figure you might not expect. Émilie du Châtelet. She was a French noblewoman, born in 1706, brilliant in mathematics and languages, and she lived in an era when women were essentially barred from universities, from academies, from the formal institutions of science. She didn't let that stop her. She studied with leading mathematicians privately. She conducted physics experiments in her home, and she embarked on what would become the definitive French translation of Newton's Principia. Not just a translation, actually, but a commentary and interpretation that made the work accessible to a much wider audience. She also made original contributions, including a crucial insight about kinetic energy. The prevailing view, following Descartes and even Newton to some extent, was that the quantity of motion, what we'd call momentum, was the fundamental measure of a moving body's effect. Du Châtelet, drawing on experiments by Willems Gravesand involving brass balls dropped into soft clay, argued that the true measure of a body's living force was proportional to the square of its velocity, not just the velocity itself. In modern terms, she was championing what we now call kinetic energy, 1/2 mass times velocity squared. And she was right. That squared relationship turns out to be fundamental. It's why a car going 60 miles an hour doesn't just do twice the damage of one going 30. It does 4 times the damage. The energy scales with the square of the speed. Du Châtelet saw this clearly, argued for it rigorously, and helped establish it in the European scientific conversation. She died in 1749, at just 42, from complications after childbirth, and her translation of the Principia was published posthumously. It remains the standard French translation to this day. Now, while the Newtonian framework was spreading and being refined, something else was happening in parallel. A whole separate thread of physics that would eventually become just as important. And this is where we start talking about energy, heat, and the laws of thermodynamics. Because Newton's laws are spectacular for describing motion, forces, acceleration, trajectories, orbits, But they don't really address some very basic questions, like what is heat? Why does a hot thing cool down? Why can't you unburn a log? Why does everything seem to run down over time? These are questions that Newton's mechanics, powerful as they are, don't naturally answer. And the story of how people figured them out is tangled up with one of the most transformative technologies in human history, the steam engine. Here's what's interesting about the relationship between science and engineering in this period. You might assume that scientists figure out the theory first, and then engineers apply it to build machines. But with the steam engine, it was almost entirely the other way around. Thomas Newcomen built a working atmospheric steam engine in 1712, a clunky, inefficient, magnificent thing used to pump water out of coal mines in England. James Watt dramatically improved it starting in the 1760s, adding a separate condenser that made it far more efficient. These machines were transforming industry, powering factories, draining mines, and eventually driving locomotives and ships. And all of this happened before anyone had a proper scientific theory of what heat actually was or why engines worked the way they did. The machines came first. The understanding came after, driven in large part by people trying to figure out why some engines were more efficient than others. The key figure here is Sadi Carnot, a young French military engineer who published a slim, remarkable book in 1824 called Reflections on the Motive Power of Fire. Carnot was only 28 years old. France had lost the Napoleonic Wars, and Carnot, whose father had been a famous general and minister of war, was acutely aware that Britain's industrial and military power was built in part on its superior steam engine technology. He wanted to understand, at the deepest level, what determined the efficiency of a heat engine. Not any particular engine, not Watt's engine or Newcomen's engine, but the ideal engine, the theoretical best that any engine could ever achieve. And what Carnot figured out is genuinely profound. He realized that a heat engine doesn't just need heat, it needs a difference in temperature. You need a hot source and a cold sink. The engine operates by taking in heat from the hot source, converting some of it into useful work, and dumping the rest into the cold sink. And here's the kicker. You can never convert all the heat into work. Some of it must always be wasted, always. Not because of friction, not because of poor design, not because of any practical limitation, but because of something fundamental about the nature of heat itself. There is a maximum possible efficiency for any heat engine, and it depends only on the temperatures of the hot source and the cold sink. The bigger the temperature difference, the more efficient the engine can theoretically be. But it can never ever reach 100%. Now Carnot worked this out using an analogy to water wheels. He imagined heat flowing from hot to cold the way water flows from high to low, doing work along the way. And he actually got some of the details wrong, because he was still working within the caloric theory, which treated heat as an invisible fluid. But his central insight, that there's a fundamental limit to efficiency, was dead right, and it survives intact in modern physics. It's essentially the second law of thermodynamics, even though it wouldn't be formulated in those terms for another few decades. Carnot died of cholera in 1832 at 36. His work was largely ignored at first, but in the 1840s and 1850s, two figures picked up the thread and wove it into something extraordinary. One was Rudolf Clausius, a German physicist. The other was William Thomson, later Lord Kelvin, a Scottish-Irish physicist and engineer. Between them, they formalized the two great laws of thermodynamics. The first law is, in some ways, the simpler one. It says that energy is conserved. It can change forms. Heat can become mechanical work. Mechanical work can become heat. Chemical energy can become electrical energy. But the total amount of energy in a closed system never changes. It's never created, never destroyed, only transformed. This sounds obvious now, but establishing it was a long, hard-fought battle. Multiple people contributed, and the priority disputes were fierce. Julius Robert von Meyer, a German physician, proposed energy conservation in 1842, based partly on observations he made while bleeding patients in the tropics. He noticed that venous blood was redder in hot climates, suggesting the body burned less fuel to maintain its temperature, which got him thinking about the relationship between heat and mechanical work. James Prescott Joule, an English brewer and amateur scientist, conducted meticulous experiments in the 1840s, most famously using falling weights to spin paddles in water and measuring the tiny temperature increase, directly establishing the mechanical equivalent of heat. Hermann von Helmholtz gave the principle its most rigorous mathematical formulation in 1847. All three have claims to the discovery, and the history is messy and human and full of bruised egos. But it's the second law that's really the deep one, the one that keeps physicists up at night. Clausius stated it in several ways, but the essence is this: heat flows spontaneously from hot to cold, never from cold to hot. That sounds almost trivially obvious. Of course, a hot cup of coffee cools down in a cold room. You've never seen a cup of coffee spontaneously heat up by drawing warmth from the cooler air around it. But think about what that means. Newton's laws of motion are completely reversible. If you film a billiard ball bouncing off a cushion and play the film backward, the reversed motion obeys Newton's laws just as well as the forward motion. There's nothing in F equals ma that distinguishes past from future. But the second law of thermodynamics does distinguish them. It gives time a direction. It says there are processes that can happen in one direction, but not the other. And that asymmetry, that one-wayness, is where our entire sense of time's arrow comes from. Clausius introduced a quantity to measure this. He called it entropy. And entropy is one of those concepts that people throw around a lot, but rarely explain well, so let's take a moment with it. Entropy is, roughly speaking, a measure of how spread out or dispersed the energy in a system is. When energy is concentrated, a hot object in a cold room, a compressed gas in one corner of a container, entropy is low. When the energy has spread out evenly, the object and the room are the same temperature, the gas fills the whole container uniformly. Entropy is high. The second law says that in any natural process, the total entropy of an isolated system either stays the same or increases. It never decreases. Things spread out. Energy disperses. Order gives way to disorder. And this isn't just about engines and heat. It's about everything. It's about why ice melts in warm water, why perfume diffuses across a room, why you can scramble an egg but never unscramble one, why buildings crumble if you don't maintain them, why every living thing eventually dies. The second law is, in some sense, the most universal and the most melancholy of all physical laws. And yet, and this is what's so beautiful, life itself seems to defy it. You exist. You're an astonishingly ordered structure, trillions of cells working in concert, maintaining low entropy locally, building complexity out of simplicity. How? Well, you do it by consuming energy from your environment and dumping waste heat back out. You're not a closed system. You're an open system, importing low entropy energy in the form of food and sunlight and exporting high entropy waste. The total entropy of you plus your environment still increases, exactly as the second law demands. But locally, temporarily, gloriously, you get to be ordered. Every living thing is a temporary pocket of low entropy, swimming against the cosmic current. That's what eating is. That's what breathing is. You're fighting the second law, and you're winning, for now. So by the middle of the 19th century, physics had two great pillars: Newtonian mechanics, governing motion and force and gravity, and thermodynamics, governing energy and heat and entropy. And they were spectacularly successful in their respective domains, but there was a whole other realm of phenomena that neither one fully addressed, a realm that had been puzzling people since the ancient Greeks rubbed amber on fur and watched it attract bits of straw: electricity, magnetism, and the slowly dawning realization that these two seemingly different forces were secretly the same thing. And this is one of those stories that unfolds slowly over decades with a cast of characters you wouldn't necessarily expect, because electricity and magnetism, for most of human history, were treated as completely separate phenomena. Electricity was the stuff of parlor tricks. You rub a glass rod with silk, and it picks up feathers. Magnetism was the stuff of compasses and lodestones, those mysterious rocks that pointed north and clung to iron. There was no obvious reason to think they had anything to do with each other. One involved sparks and shocks and static cling. The other involved invisible forces that made needles swing. Different things, obviously. Except they weren't. And the first person to really demonstrate the connection was a Danish physicist named Hans Christian Ørsted. And the way he discovered it is one of those beautiful accidents that could only happen to someone who was already paying attention. It was 1820, and Ørsted was giving a lecture, actually standing in front of students, demonstrating electrical experiments, when he noticed something strange. He had a compass sitting on his lecture table, and when he ran an electric current through a wire nearby, the compass needle twitched. It moved. Not a lot, but it moved. And Ørsted, to his enormous credit, didn't ignore it. He didn't write it off as a vibration from the table or a draft in the room. He stopped, and he investigated. What he found was remarkable. When electric current flowed through a wire, it created a magnetic field around that wire, not just near the wire, around it, in circles. The compass needle didn't point toward the wire or away from it. It pointed perpendicular to it, trying to align with invisible circular lines of force that wrapped around the current like rings around a finger. Think about that. Electricity flowing through a wire spontaneously generates magnetism. These two phenomena that everyone had treated as completely unrelated were, in fact, intimately connected. Now, news traveled fast in the scientific world of the 1820s, not internet fast, but letter and journal fast. And within weeks of Ørsted's announcement, physicists across Europe were scrambling to understand what this meant. And one of the people who grabbed hold of this thread and pulled harder than anyone else was André-Marie Ampère in France. Ampère was a fascinating person, largely self-taught, deeply passionate, and capable of working at a ferocious pace when something caught his attention. Within a week of hearing about Ørsted's discovery, Ampère had worked out the mathematics describing the relationship between electric currents and the magnetic forces they produce. He showed that two parallel wires carrying current would attract or repel each other depending on which direction the currents flowed. And that's a purely magnetic interaction, generated entirely by electricity. He essentially proved that magnetism could be created from scratch just by moving electric charge. No lodestones required. But here's the thing. Ørsted and Ampère had shown that electricity produces magnetism. The natural question, the beautiful question, was, does it work the other way around? Can magnetism produce electricity? And this is where Michael Faraday enters the story. And honestly, Faraday might be the most remarkable figure in the entire history of physics. His story is almost too good to be true. Born in 1791 in South London, the son of a blacksmith, Faraday had almost no formal education. He left school at 13 to work as a bookbinder's apprentice, but he read the books he was binding, especially the science books, and he became obsessed with chemistry and electricity. He attended publics, lectures by the famous chemist Humphrey Davy at the Royal Institution, took meticulous notes, bound them into a beautiful volume, and sent them to Davy asking for a job. Davy eventually hired him as a laboratory assistant, essentially a glorified bottle washer. And from that position, through sheer brilliance, persistence, and an almost supernatural intuition for how nature works, Faraday became one of the greatest experimental scientists who ever lived. Faraday didn't have the mathematical training of someone like Ampere. He couldn't write down equations the way the French and German physicists could. But he had something else. He could see things. He thought in pictures, in physical intuitions, in spatial relationships. And in 1831, after years of trying, he cracked the problem. He discovered electromagnetic induction. He showed that a changing magnetic field, not a static one, but one that's moving or growing or shrinking, produces an electric current in a nearby conductor. Push a magnet through a coil of wire, and current flows. Pull it out, and current flows the other way. Stop moving the magnet, and the current stops. It's the change that matters, the motion, the variation over time. And this discovery, let's just sit with this for a moment. This is the principle behind essentially every electrical generator on the planet. Every power plant, whether it burns coal, splits atoms, captures wind, or harnesses falling water, ultimately works by spinning magnets inside coils of wire, or spinning coils of wire inside magnets. That's it. That's the fundamental mechanism. Faraday's discovery in 1831 is the reason you have electricity in your home right now, the reason your lights work, your phone charges, your refrigerator hums. It all goes back to a bookbinder's apprentice pushing a magnet through a loop of copper wire and watching a needle deflect on a meter. But Faraday did something else, something more conceptually radical, that doesn't get enough credit. He invented the idea of the field. Before Faraday, people thought about forces the way Newton had, as actions at a distance. The sun pulls on the earth somehow, across 93 million miles of empty space. A magnet attracts iron somehow, across the gap between them. Nobody was very comfortable with this, Newton included. Remember, he'd explicitly said he wouldn't speculate about the mechanism. But Faraday proposed something different. He said, what if space isn't empty? What if the magnet fills the space around it with something, an invisible entity, a condition of space itself? And it's this thing, this field, that exerts the force. The iron doesn't feel the magnet directly. It feels the field that the magnet has created in the space where the iron sits. Now, you might think that's just a semantic trick, just relabeling action at a distance as action through a field. But it's not. It's a profound shift in thinking. Because fields have properties. They have structure. They store energy. They can propagate. And once you start thinking in terms of fields rather than forces acting at a distance, the whole picture changes. Faraday would sprinkle iron filings around a magnet and watch them arrange themselves into beautiful curved lines. And he said those lines are real. Those are the lines of force. The field is a physical thing, filling space, carrying energy, mediating interactions. Most of the mathematically trained physicists of his era thought this was a bit naive, a bit too visual, a bit too hand-wavy for rigorous science. They were wrong. Faraday was seeing something that the equations hadn't yet caught up to. And the person who made the equations catch up was James Clerk Maxwell. If Newton unified heaven and earth, Maxwell unified electricity, magnetism, and, astonishingly, light. And he did it with 4 equations, just 4. They're called Maxwell's equations, and they are, by any reasonable measure, among the most beautiful and consequential achievements in the history of human thought. Maxwell was Scottish, born in Edinburgh in 1831, the same year Faraday discovered induction, which feels almost poetic. He was a prodigy, publishing his first scientific paper at 14, and he had exactly the mathematical gifts that Faraday lacked. What Maxwell did, starting in the late 1850s and culminating in his great treatise of 1873, was take all the experimental discoveries of Ørsted, Ampere, Faraday, and others and weave them into a single, unified mathematical framework. 4 equations that describe everything about how electric and magnetic fields behave, how they're created by charges and currents, and, here's the key, how they create each other. Because that's what Maxwell's equations reveal. A changing electric field produces a magnetic field. A changing magnetic field produces an electric field. Faraday had shown the second part experimentally. Maxwell added the first part as a theoretical insight, a term he called the displacement current, and when he put it all together, something extraordinary fell out of the math. The equations predicted that coupled electric and magnetic fields could sustain each other, leapfrogging through space. The changing electric field creating a magnetic field, the changing magnetic field creating an electric field, on, propagating outward as a wave, an electromagnetic wave. And Maxwell could calculate the speed of this wave from the equations. It depended on 2 constants, the permittivity and permeability of free space, which had been measured in laboratory experiments on static electricity and magnetism. When he plugged in the numbers, the speed came out to approximately 310,000 kilometers per second. And the measured speed of light, which had been determined through completely independent astronomical and optical experiments, was approximately 315,000 kilometers per second. The agreement was too close to be coincidence. Maxwell wrote, with characteristic understatement, that they could scarcely avoid the inference that light itself is an electromagnetic wave. Think about what just happened. Electricity, magnetism, and light, 3 phenomena that had seemed completely unrelated for all of human history, turned out to be manifestations of the same underlying thing. The spark from rubbing amber, the pull of a compass needle, the light from a candle, all electromagnetic phenomena, all described by the same 4 equations. This is unification on a breathtaking scale, and Maxwell predicted that electromagnetic waves could exist at any frequency, not just the frequencies our eyes happen to detect. There should be waves with longer wavelengths than visible light, and shorter ones too. This was a pure prediction from the theory. No one had ever detected such waves, and Maxwell didn't live to see the confirmation. He died in 1879, at just 48, of abdominal cancer, the same disease that had killed his mother at the same age. But in 1887, 8 years after Maxwell's death, a German physicist named Heinrich Hertz built an apparatus that did exactly what the theory predicted. He generated electromagnetic waves in his laboratory using oscillating electric circuits, detected them across the room with a simple loop of wire, and showed that they behaved exactly like light. They reflected, refracted, could be polarized, traveled at the speed of light. Maxwell was right. Electromagnetic waves were real, and those waves Hertz generated in his lab, those were what we now call radio waves. Within a decade, Guglielmo Marconi, would figure out how to use them to send messages across distances, and the entire age of wireless communication, radio, television, radar, Wi-Fi, cell phones, Bluetooth, GPS, everything, traces its ancestry directly back to Maxwell's equations and Hertz's tabletop experiment. So now the picture of physics, as the 19th century draws toward its close, has expanded enormously. 3 great pillars: Newtonian mechanics for motion and gravity, thermodynamics for energy and entropy, and Maxwell's electromagnetism for light, electricity, and magnetism. And they work. They work spectacularly well. Bridges are built, engines are designed, telegraphs span oceans, all on the strength of these theories. In 1900, the great physicist Lord Kelvin, the same William Thomson who helped formalize thermodynamics, is often quoted as saying that physics was essentially complete, with only 2 small clouds on the horizon. Whether he actually said exactly that is debated, but the sentiment was real. Many physicists felt that the fundamental laws were known, and all that remained was to work out the details, measure things more precisely, push the decimal places further. Those 2 small clouds, though, they were about to become hurricanes. One cloud was the puzzling result of the Michelson-Morley experiment, which tried to detect Earth's motion through the luminiferous ether, the hypothetical medium that everyone assumed electromagnetic waves must travel through, the way sound waves travel through air. They couldn't find it. No matter how they oriented their apparatus, no matter what time of year they measured, the speed of light was always the same, always, in every direction. As if the Earth weren't moving at all, which was obviously absurd. Something was deeply wrong with the picture. The other cloud was the problem of black body radiation, the way hot objects glow. Classical physics predicted that a perfectly absorbing body should radiate infinite energy at short wavelengths, a result so clearly wrong it was called the ultraviolet catastrophe. The equation said a glowing fireplace poker should blast you with infinite ultraviolet and X-ray radiation. It obviously didn't, but no one could figure out where the math went wrong. And these 2 little clouds, these 2 nagging inconsistencies at the edges of an otherwise triumphant physics, were about to blow the entire edifice apart. Because the resolution of the first cloud would lead to Einstein's special theory of relativity, and the resolution of the second would lead to quantum mechanics. And between them, these 2 revolutions would reshape everything physicists thought they knew about space, time, matter, and energy. And they'd do it in the span of about 30 years, roughly 1900 to 1930, a single generation that would dismantle a worldview that had stood for over 2 centuries. Let's start with the second cloud first, the ultraviolet catastrophe, because chronologically, that's where the first crack appeared. And it appeared in the most unlikely way, not with a grand philosophical insight, but with a mathematical trick that its inventor didn't even fully believe. The year is 1900. The physicist is Max Planck, a German professor in Berlin, and he's been wrestling with this black body radiation problem for years. He's a conservative, careful man, not the type to overthrow physics. He actually chose physics despite being warned by one of his professors that there was nothing important left to discover. Imagine that. He went into it anyway because he loved it. And now, at the age of 42, he's staring at experimental curves that show how much energy a hot object radiates at each wavelength, and he cannot make classical physics reproduce those curves. Nobody can. The equations blow up at short wavelengths, predicting infinite energy where experiments show the radiation actually drops off to 0. So Planck does something desperate. he introduces a mathematical assumption that he himself considers a trick, a computational convenience. He proposes that energy isn't emitted continuously, the way classical physics assumes, but in tiny discrete packets. He calls them quanta. Each quantum of energy is proportional to the frequency of the radiation, linked by a new constant that we now call Planck's constant, usually written as the letter h. It's an incredibly small number, about 6.626 times 10 to the negative 34 joule seconds, unimaginably tiny. But it's not zero, and that makes all the difference. Here's why. If energy can only come in these little packets, then at very high frequencies, short wavelengths, the ultraviolet end, each individual quantum carries a lot of energy. So much energy, in fact, that the atoms in the hot object simply can't muster enough to emit many of them. The radiation at short wavelengths gets suppressed naturally. The catastrophe vanishes. The math works. Planck's formula matches the experimental curves perfectly. But here's the thing. Planck doesn't really believe what he's done. He thinks the quantization is a mathematical trick, an artifact of the calculation method. He spends years trying to derive the same result without the quantum assumption. He can't. Nobody can. Because it's not a trick. It's a clue. A clue that nature, at its most fundamental level, doesn't work the way anyone expected. Now, the person who takes that clue and runs with it, who actually says, "No, this quantization is real, it's physical, it's telling us something profound about the universe," is a 26-year-old patent clerk in Bern, Switzerland, and you already know his name. Albert Einstein, in 1905, publishes 4 papers that would each individually have made him one of the most important physicists in history. 4 papers in 1 year. It's sometimes called his miracle year, his annus mirabilis. And one of those papers is about the photoelectric effect, and it's the one that takes Planck's quantum idea and pushes it further than Planck ever dared. The photoelectric effect is this. When you shine light on certain metals, electrons get knocked loose. That much was known. But the details were strange. Classical wave theory predicted that brighter light should give the ejected electrons more energy. You're hitting them with a bigger wave after all. But that's not what happened. Brighter light knocked out more electrons, but each individual electron had the same energy, regardless of brightness. What did change the energy of each electron was the color of the light, its frequency. Higher frequency, more energetic electrons. Below a certain frequency, no electrons at all, no matter how bright the light. Einstein's explanation was breathtakingly simple and breathtakingly radical. Light, he said, isn't just a wave, it actually comes in discrete packets, quanta of light, which we now call photons. Each photon carries an energy equal to Planck's constant times the frequency. When a photon hits an electron, it transfers its energy in one lump. If that lump is big enough, if the frequency is high enough, the electron escapes. If it's not, the electron stays put, no matter how many low-energy photons you throw at it. Brightness just means more photons, not more energetic ones. Think about that for a second. Maxwell had shown convincingly and beautifully that light is an electromagnetic wave. Interference, diffraction, polarization, all wave phenomena, all perfectly explained. And now Einstein is saying light is also a particle, not instead of a wave. Also, both at once. This is the beginning of wave-particle duality, and it's going to get stranger before it gets less strange. Actually, it never really gets less strange. Physicists just get more comfortable with the strangeness. And here's what's fascinating. The Nobel Prize Committee. When they finally gave Einstein the Nobel Prize in 1921, They gave it to him for the photoelectric effect. Not for relativity, the photoelectric effect. Because that's the work that had been most thoroughly confirmed by experiment at that point, and because, frankly, relativity was still controversial in some circles. But we'll come back to relativity in a moment. First, let's stay with the quantum story a little longer, because it gets wilder. In 1913, a young Danish physicist named Niels Bohr applies quantum ideas to the structure of the atom. At this point, the best model of the atom is Ernest Rutherford's, a tiny, dense nucleus surrounded by orbiting electrons, like a miniature solar system. But there's a fatal problem with this picture. According to Maxwell's equations, an orbiting electron is an accelerating charge, and accelerating charges radiate electromagnetic energy. So the electron should continuously lose energy, spiral inward, and crash into the nucleus in a fraction of a second. Every atom should be unstable. Every atom should collapse almost instantly. Obviously, they don't. You're made of atoms. They're doing fine. Bohr's solution is to simply declare, and this takes real audacity, that electrons can only orbit at certain specific distances from the nucleus, corresponding to specific energy levels. They can jump between these levels by absorbing or emitting a photon of exactly the right energy, exactly the right frequency. But they cannot exist between the levels. They cannot spiral. They're quantized, just like Planck's energy packets. And when Bohr works out the math for hydrogen, the simplest atom, his predicted energy levels match the observed spectral lines, the specific colors of light that hydrogen emits, with stunning precision. It works. But it's also, honestly, a bit of a hack. Bohr can't explain why the electrons are restricted to those orbits. He just asserts it. The deeper explanation won't come for another decade, and when it does, it'll be even more unsettling. But let's pause here and deal with that other cloud, the Michelson-Morley result and the speed of light. Because this is where Einstein's other revolution comes in, and it happens in the same miraculous year of 1905. Remember the problem. Light travels at a specific speed, about 299,792 kilometers per second in a vacuum. Maxwell's equations predict this speed, and it falls out of the math as a constant, determined by the electric and magnetic properties of empty space. But a constant relative to what? If you're on a train and you throw a ball forward, someone on the ground sees the ball moving at the speed of your throw plus the speed of the train. That's how velocities add. So if light is a wave moving through the ether, and the Earth is moving through the ether, you should be able to detect the difference. Light should appear to move slightly faster in one direction than another, depending on how the Earth is moving relative to the ether. Michelson and Morley built an extraordinarily precise interferometer to detect exactly this difference. They split a beam of light, sent the two halves in perpendicular directions, bounced them off mirrors, and recombined them. If light traveled at different speeds in different directions, the two beams would be slightly out of step when they recombined, creating an interference pattern that would shift as the apparatus was rotated. They could detect differences in the speed of light as small as a few kilometers per second. The expected difference, based on Earth's orbital speed around the Sun, was about 30 kilometers per second, easily detectable. They found nothing. Zero. No shift. The speed of light was the same in every direction, at every time of year. It was as if the Earth were standing perfectly still in the ether, which made no sense at all. Various physicists tried to patch things up. The Dutch physicist Hendrik Lorentz and the Irish physicist George Fitzgerald independently proposed that objects moving through the ether physically contract in the direction of motion. They literally get shorter. by just the right amount to cancel out the expected effect. It was clever, and mathematically it worked, but it felt ad hoc. Why would motion through the ether cause physical contraction? What mechanism could possibly explain that? Einstein's approach was completely different, and it was stunning in its simplicity. Instead of trying to save the ether, he threw it out entirely. He started with two postulates, just two. First, the laws of physics are the same in all inertial reference frames. No experiment you can do in a smoothly moving laboratory will tell you whether you're moving or standing still. Second, the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. That second postulate sounds innocent, but think about what it means. If you're standing still, and I'm flying past you at half the speed of light, and we both measure the speed of the same beam of light, we get the same answer. Not different answers adjusted by our relative velocity. The same answer. That completely violates our everyday intuition about how speeds add up. And Einstein showed that if you take those two postulates seriously, really seriously, following the math wherever it leads, you're forced to conclude that space and time themselves are not what we thought they were. Time passes at different rates for observers moving at different speeds. Lengths contract in the direction of motion. Two events that are simultaneous for one observer are not simultaneous for another. Mass and energy are equivalent, related by the most famous equation in all of physics, E equals mc squared, where c is the speed of light, and because c is such an enormous number, even a tiny amount of mass corresponds to a staggering amount of energy. This is special relativity. Special because it deals with the special case of uniform motion, no acceleration, no gravity, and it's not a minor correction to Newtonian mechanics. At everyday speeds, the differences are negligible, which is why Newton's laws work so well for baseballs and bridges and planets. But as you approach the speed of light, the effects become dramatic. Time dilation, length contraction. These aren't optical illusions or measurement artifacts. They're real. They've been confirmed by countless experiments. Atomic clocks flown on jets run slightly slower than identical clocks on the ground, by exactly the amount Einstein predicted. Particles called muons, created in the upper atmosphere by cosmic rays, live long enough to reach the Earth's surface only because time dilation stretches their brief lifetimes as seen from our reference frame. And here's something that might help you appreciate just how radical this was. Newton's laws had reigned for over 200 years. They'd sent cannonballs along predicted trajectories, explained the tides, predicted the existence of Neptune. They were the most successful scientific theory in human history. And Einstein, at 26, working alone in a patent office, showed that they were incomplete. Not wrong, exactly. They're a brilliant approximation that works perfectly well at low speeds, but incomplete. The universe, at its deepest level, plays by different rules than Newton imagined, and Einstein wasn't done, because special relativity only handles uniform motion, and the real universe is full of acceleration and gravity. It took him another 10 years of grueling mathematical work, false starts, moments of despair, and at least one period where he published equations he later realized were wrong. But in 1915, he unveiled the general theory of relativity. And this one changed everything all over again, because where special relativity had reimagined time and space, general relativity reimagined gravity itself. And what Einstein proposed was, honestly, one of the most beautiful ideas any human being has ever had. Here's the setup. Newton told us that gravity is a force. The earth pulls the apple, the sun pulls the earth, and this force acts instantaneously across empty space. Newton himself was uncomfortable with that. Action at a distance, he called it, and he admitted he had no mechanism for it. He just knew the math worked. But Einstein, fresh off discovering that nothing can travel faster than light, saw a problem. If the sun suddenly vanished, Newton's gravity would say the Earth instantly flies off in a straight line, because the gravitational force disappears everywhere all at once. But that violates the speed limit. Information, even gravitational information, can't travel faster than light. So something about Newton's picture had to be wrong. And then Einstein had what he later called the happiest thought of his life. He was sitting in the patent office in Bern, probably in 1907, and he imagined a person falling off a roof. And he realized that while you're falling, you don't feel your own weight. You're accelerating toward the ground, sure, but in your own little falling reference frame, you feel weightless. It's the same sensation astronauts experience in orbit. They're actually falling around the Earth continuously, and that's why they float. Einstein realized this meant something profound. There's no experiment you can do inside a closed box to tell the difference between floating in deep space, far from any gravity, and free falling in a gravitational field. Gravity and acceleration are, in some deep sense, the same thing. He called this the equivalence principle, and it became the foundation stone of general relativity. Now, building on that insight took him those 10 grueling years. He needed mathematics that didn't even exist yet in physics, a branch of geometry called Riemannian geometry, developed decades earlier by the mathematician Bernhard Riemann. And Einstein struggled with it. He collaborated with his old classmate, Marcel Grossmann, who was a mathematician and could help him with the formalism. There were wrong turns. In 1913, Einstein and Grossmann published a theory that was almost right, but not quite. The field equations weren't fully covariant, meaning they didn't work the same way in all coordinate systems, which violated the very principle Einstein was trying to embody. He spent 2 more years fixing it, and in November 1915, he presented his final field equations to the Prussian Academy of Sciences. And those equations said something that still gives me chills when I think about it carefully. They said that mass and energy don't pull on things through some mysterious force reaching across space. Instead, mass and energy curve the fabric of spacetime itself, and objects moving through that curved spacetime follow the straightest possible paths, called geodesics, which, in curved geometry, aren't straight at all. They're curves. The Earth doesn't orbit the Sun because an invisible rope is pulling it in a circle. The Earth orbits the Sun because the Sun's enormous mass warps the space-time around it into a kind of curved geometry, and the Earth is simply following the straightest path available to it through that warped landscape. It's rolling along the contours of curved space-time. Think about that for a second. Gravity isn't a force at all in Einstein's picture. It's geometry. It's the shape of the universe itself, bent and curved by everything that has mass or energy. And things move through that shape, the way a marble rolls on a curved surface. The analogy people often use is a bowling ball on a trampoline. You place a heavy bowling ball in the center, and the surface dips. Roll a smaller ball nearby, and it curves toward the bowling ball, not because there's a force pulling it, but because the surface it's rolling on is curved. That analogy isn't perfect. It's 2-dimensional, and real space-time curvature is 4-dimensional and more subtle. But it captures the essential flavor. The mass tells space-time how to curve. The curvature tells objects how to move. The physicist John Wheeler summed it up in a line that's become famous. Spacetime tells matter how to move, and matter tells spacetime how to curve. And here's what's really clever about this. Einstein's equations didn't just reproduce everything Newton's gravity could do. They did more. They made new predictions. Predictions that Newton's theory couldn't. The very first one Einstein checked was the orbit of Mercury. Mercury's orbit has a slight anomaly. Its elliptical path slowly rotates around the Sun, a phenomenon called the precession of the perihelion. Newtonian gravity, accounting for the gravitational influence of all the other planets, predicted most of this precession, but not all of it. There was a leftover discrepancy of about 43 arc-seconds per century. A tiny amount, but astronomers had known about it since the 1850s, and it was a genuine puzzle. When Einstein plugged Mercury's orbit into his new field equations, the answer came out to exactly 43 arc-seconds per century. He later said that when he saw that result, he had heart palpitations. He knew his theory was right. The second prediction was even more dramatic. Einstein's equations said that light itself should be bent by gravity, that a beam of light passing near a massive object should curve, because the spacetime the light travels through is curved. And he calculated exactly how much starlight should be deflected as it passed near the Sun. The British astronomer Arthur Eddington organized expeditions to observe a total solar eclipse on May 29, 1919, from two locations, the island of Principe off the west coast of Africa and Sobral in northern Brazil. During the eclipse, when the sun's glare was blocked by the moon, they photographed the stars near the sun's edge and compared their apparent positions to where those stars normally appeared in the night sky. The results, announced in November 1919, confirmed Einstein's prediction. The stars appeared slightly shifted by the amount general relativity predicted, roughly 1.75 arc-seconds for starlight just grazing the sun's edge. The news made front pages around the world. Einstein became, essentially overnight, the most famous scientist alive. But general relativity predicted more than bent starlight. It predicted that time itself runs slower in stronger gravitational fields. A clock at sea level ticks slightly slower than an identical clock on a mountaintop, because the gravitational field is slightly stronger at sea level. This is gravitational time dilation, and it's different from the velocity-based time dilation of special relativity, though both effects are real and both matter in practice. And here's where it connects to your everyday life, in a way you might not expect. The GPS satellites orbiting the Earth carry atomic clocks, and those clocks are affected by both kinds of time dilation. They're moving fast, so special relativity makes them tick slightly slower, but they're also higher up in Earth's gravitational field, where gravity is weaker, so general relativity makes them tick slightly faster. The two effects don't cancel. The gravitational effect is larger, and if engineers didn't correct for both relativistic effects, GPS positions would drift by about 10 kilometers per day. Your phone would tell you you're in the wrong city, so every time you use GPS to navigate, you're relying on Einstein's general relativity being correct. It's not abstract philosophy, it's practical engineering. General relativity also predicted things that seemed outlandish at the time. Gravitational waves, ripples in the fabric of spacetime itself, spreading outward from accelerating masses the way ripples spread on a pond when you toss in a stone. Einstein predicted them in 1916, but he thought they'd be so incredibly faint that no one would ever detect them. He was almost right about that. It took a century. In September 2015, the LIGO Observatory, two enormous L-shaped detectors, one in Louisiana and one in Washington state, each with arms 4 kilometers long, detected gravitational waves for the first time. The waves came from 2 black holes, each about 30 times the mass of the Sun, spiraling into each other and merging about 1.3 billion light-years away. The signal matched the predictions of general relativity with extraordinary precision. The distortion those waves caused in the detector arms was about 1,000th the diameter of a proton. 1,000th the diameter of a proton. The engineering required to measure something that small is almost incomprehensible, and the fact that the signal matched Einstein's 100-year-old prediction is one of the great triumphs of physics. And then there are black holes, regions where space-time is curved so extremely that nothing, not even light, can escape. The concept emerged from Einstein's equations almost immediately. In 1916, the German physicist Karl Schwarzschild, while serving on the Eastern Front in World War I, found an exact solution to Einstein's field equations describing the space-time around a perfectly spherical, non-rotating mass. That solution contained a mathematical boundary, what we now call the event horizon, beyond which escape is impossible. Schwarzschild died just months later from an autoimmune disease contracted in the trenches. He never knew what his solution would come to mean. Einstein himself didn't believe black holes could actually exist in nature. He thought they were mathematical curiosities, artifacts of the equations that the real universe would somehow avoid. But the real universe had other plans. We've now observed black holes indirectly through their effects on nearby matter, and directly through gravitational waves from merging black holes. In 2019, the Event Horizon Telescope collaboration produced the first image of a black hole's shadow. The supermassive black hole at the center of the galaxy, M87, about 6.5 billion times the mass of the Sun. General relativity predicted what that shadow should look like, and the image matched. So, let's step back for a moment and appreciate where we are. By 1915, Einstein had given us 2 theories, special relativity and general relativity, that completely replaced Newton's framework for understanding space, time, and gravity. Not discarded it, exactly. Newton's laws are still there, still incredibly useful, still the right tool for engineering bridges and launching rockets within the solar system. But they're now understood as approximations, brilliant, practical approximations that emerge from the deeper relativistic framework when speeds are low and gravitational fields are weak. Meanwhile, on the quantum side of things, the revolution was accelerating. Remember how Bohr's model of the atom worked beautifully for hydrogen, but couldn't explain more complex atoms? By the early 1920s, physicists knew they needed something deeper. And what came next, in a burst of creativity between roughly 1925 and 1927, was one of the strangest and most powerful theories ever constructed. It started with a young French aristocrat named Louis de Broglie, who in his 1924 doctoral thesis proposed something that sounded almost absurd. If light, which everyone had thought was a wave, could behave like a particle, as Einstein had shown with the photoelectric effect, then maybe particles, like electrons, could behave like waves. He even wrote down a formula for the wavelength of a particle, relating it to its momentum through Planck's constant. His thesis committee wasn't sure what to make of it. They sent it to Einstein, who replied that de Broglie had lifted a corner of a great veil, and within a few years, experiments confirmed it. Electrons fired through crystals produced diffraction patterns, patterns that only waves can make. Matter itself had a wave nature. And that discovery opened a door that led somewhere no one expected. Because what Schrödinger and Heisenberg built in the months that followed wasn't just a better model of the atom. It was a fundamentally new way of understanding reality. One that, almost a century later, still unsettles people who think about it carefully. Let's start with Heisenberg, because his story is wonderfully dramatic. Werner Heisenberg was a young German physicist, barely 23 years old in the summer of 1925, and he was suffering from terrible hay fever. So bad, in fact, that he fled to Helgoland, a tiny rocky island in the North Sea, with almost no pollen, to recover. And there, essentially alone on this barren island, working through the nights, he created something extraordinary. He built a mathematical framework for quantum mechanics that abandoned the very idea of trying to picture what an electron is doing inside an atom. Forget orbits, forget trajectories, forget asking where the electron is at any given moment. Instead, Heisenberg focused entirely on what you can actually observe: the frequencies and intensities of light that atoms emit and absorb. He organized these observable quantities into arrays of numbers, grids of numbers, and worked out rules for how they combine. When he multiplied two of these arrays together, he discovered something strange. The order of multiplication mattered. A times B did not equal B times A. That might sound like a minor mathematical quirk, but it turned out to be one of the most profound clues in the history of physics. Heisenberg brought his work back to Göttingen, and his mentor Max Born recognized immediately what those arrays were. They were matrices, a well-known mathematical structure. Born, along with his student Pascual Jordan, helped Heisenberg formalize the whole thing into what became known as matrix mechanics. It was rigorous, it was powerful, and it gave correct predictions, but it was also, frankly, almost impossible to visualize. There was no picture to hold in your head. It was pure abstraction, pure mathematics, and most physicists found it deeply uncomfortable. Which is exactly why what happened next was so remarkable. Because just a few months later, in early 1926, an Austrian physicist named Erwin Schrödinger came at the same problem from a completely different direction and arrived at something that looked, on the surface, entirely different. Schrödinger loved de Broglie's idea of matter waves. He took it seriously, literally seriously. If an electron is a wave, he reasoned, then there should be a wave equation governing its behavior, just as there are wave equations for sound and light and water. And over Christmas of 1925, during a holiday in the Swiss Alps, reportedly in the company of a woman who was not his wife, a detail that physicists love to mention, Schrödinger found that equation. The Schrödinger equation. You've probably heard the name even if you've never seen the math. It's one of those equations that sits alongside Newton's second law and Maxwell's equations in the pantheon of physics. And what it does is describe how a quantity called the wave function evolves over time. The wave function is usually written with the Greek letter psi, and it's a mathematical object that contains, in principle, everything you can know about a quantum system. Give me the wave function of an electron in a hydrogen atom, and I can calculate the probability of finding that electron at any particular location, the energy it might have, how it will respond to a magnetic field, everything. But here's where it gets philosophically strange, and this is worth slowing down for. The wave function doesn't tell you where the electron is. It tells you the probability of finding it in various places if you look. Before you measure, the electron doesn't have a definite position. It's not that we don't know where it is and just need a better instrument. According to quantum mechanics, the question, "Where is the electron right now?" simply doesn't have an answer until you perform a measurement. The electron exists in what's called a superposition. a combination of many possible states simultaneously. And when you measure, the wave function collapses, and you get one definite result. Now, you might be thinking, that can't be right. Surely the electron is somewhere, and we just don't know where. That was Einstein's instinct too, and it bothered him for the rest of his life. But every experiment ever performed has confirmed the quantum mechanical prediction. The probabilities are real. The indeterminacy is fundamental. It's not a gap in our knowledge, it's a feature of nature itself. And here's the thing that tied the whole picture together. In 1926, Schrödinger proved that his wave mechanics and Heisenberg's matrix mechanics, despite looking completely different, were mathematically equivalent. They were the same theory expressed in two different languages. That was a stunning result. Two physicists, working independently, using different mathematical tools and different physical intuitions, had arrived at the same underlying structure. That kind of convergence gives you real confidence that you're on to something true. But the interpretation, what does it all mean? That was far from settled. And this is where Heisenberg dropped another bombshell. In 1927, he published his uncertainty principle. And it's one of those ideas that has seeped so deeply into popular culture that almost everyone has heard of it, even if the actual physics gets garbled along the way. So let's get it right. The uncertainty principle says that there are pairs of physical quantities, position and momentum being the most famous pair, that cannot both be known precisely at the same time. The more precisely you pin down where a particle is, the less precisely you can know how fast it's moving, and vice versa. This isn't about clumsy measurements or imperfect instruments. It's a fundamental limit built into the fabric of reality. It falls directly out of the mathematics of wave functions, and it's connected to that strange non-commutativity that Heisenberg discovered back on Helgoland, the fact that the order of operations matters. Think about it this way. If a particle is genuinely described by a wave, then a wave that has a very precise position, a sharp spike, must be built by adding together many different wavelengths, which means many different momenta. And a wave with a very precise wavelength, a single pure tone, stretching out smoothly, is spread out over a huge region of space, so its position is completely undefined. You can't have a wave that's both perfectly localized and perfectly pure in frequency. It's not a limitation of your measuring device. It's what it means to be a wave. The same year, 1927, most of the key players gathered in Brussels for the 5th Solvay conference, and the photograph from that meeting is one of the most famous images in the history of science. 29 physicists, 17 of whom were or would become Nobel laureates. Einstein, Bohr, Heisenberg, Schrödinger, Born, Dirac, Pauli, Curie, Lorentz, Planck, all in one room. And they argued. They argued passionately about what quantum mechanics meant. Bohr and Heisenberg championed what became known as the Copenhagen interpretation. The wave function is the complete description of a quantum system. Probabilities are fundamental, and asking what happens between measurements is meaningless. Einstein pushed back hard. He kept proposing clever thought experiments designed to show that quantum mechanics must be incomplete, that there must be some deeper, deterministic reality underneath. And each time, Bohr found the flaw in Einstein's argument. The debates between Einstein and Bohr at the Solvay conferences are legendary. Two of the greatest minds in history going back and forth, probing the foundations of reality itself. Einstein never accepted the Copenhagen interpretation. His famous line, often paraphrased as "God does not play dice," captures his conviction that the universe must be deterministic at its core. But as the decades passed, Quantum mechanics kept working. It predicted the outcomes of experiments with astonishing precision. It explained the periodic table, the behavior of semiconductors, the structure of molecules, the mechanism of radioactive decay. It became the foundation for transistors, lasers, MRI machines, nuclear energy. Every piece of modern technology that depends on understanding matter at the atomic scale, which is essentially all modern technology, rests on the framework that Heisenberg, Schrödinger, Born, Dirac, and their colleagues built in that extraordinary burst between 1925 and 1927. And there's one more piece from this era that deserves attention because it connects quantum mechanics to the everyday world in a way that's easy to overlook. In 1925, Wolfgang Pauli, brilliant, sharp-tongued, famously difficult to impress, proposed what's now called the Pauli exclusion principle. It says that no two electrons in an atom can occupy the same quantum state simultaneously. That might sound like a technical detail, but think about what it means. It's the reason the periodic table has the structure it does. It's the reason atoms have distinct chemical properties. It's the reason matter is solid, why your hand doesn't pass through the table. Without the exclusion principle, all electrons would collapse into the lowest energy state. Every atom would behave the same way, and chemistry as we know it simply wouldn't exist. You wouldn't exist. The rigidity of the chair you're sitting in, the diversity of materials in the world around you, the fact that matter takes up space at all, it all traces back to this one quantum rule. So by the late 1920s, physics had been completely transformed. In barely 3 decades, from Planck's desperate hypothesis in 1900 to the mature formalism of quantum mechanics by 1927 or so, the understanding of nature at its most fundamental level had undergone a revolution more radical than anything since Newton. And the strange thing, the thing that still catches people off guard, is that the two great pillars of modern physics, general relativity and quantum mechanics, are each spectacularly successful in their own domain, but they don't fit together. General relativity describes gravity as the curvature of smooth, continuous spacetime. Quantum mechanics describes the other forces and all matter in terms of discrete quanta and probabilistic wave functions. When you try to apply quantum mechanics to gravity itself, when you try to write down a quantum theory of the gravitational field, the mathematics breaks down. You get infinities, nonsensical answers, predictions that don't make sense. This isn't just a technical inconvenience. It means that in situations where both gravity and quantum effects are important, at the center of a black hole, or in the first instant of the Big Bang, our current theories simply cannot tell us what happens. And that tension, that unresolved gap between the two deepest theories we have, has driven an enormous amount of theoretical physics over the last century. String theory, loop quantum gravity, various other approaches, they're all attempts to find the deeper framework that contains both general relativity and quantum mechanics as special cases, the way general relativity contains Newton's gravity as a special case. But even without that final unification, what we have is extraordinary. And there's a beautiful pattern here, one that connects everything we've been talking about tonight. Each revolution in physics didn't destroy what came before. It revealed it as an approximation, a special case of something deeper. Newton's laws are contained within Einstein's. Classical physics emerges from quantum mechanics when you zoom out to large scales. The old laws don't become wrong. They become understood. You see their boundaries, their edges, the places where they start to blur. And beyond those edges, you find something wider, something more encompassing, something that holds the older truth inside it, like a smaller room, inside a larger house. And that pattern, that nesting, is one of the most remarkable things about physics as a whole. It suggests that the universe isn't chaotic in the way it reveals itself to us. There's a coherence to it, a layered structure, as if each time we peel back one curtain, the next curtain is already there, waiting, and behind it is a view that's more expansive than anything we imagined from the room we were standing in before. So let's sit with that for a moment. Let's think about where we actually are, right now, in the story of physics. Because it's a strange and wonderful place to be. We have general relativity, which tells us that mass and energy curve the fabric of spacetime, and that this curvature is what we experience as gravity. It works beautifully for planets, stars, galaxies, the expansion of the universe itself. We have quantum mechanics, which tells us that at the smallest scales, nature is grainy, probabilistic, and deeply strange. Particles don't have definite positions until measured. Energy comes in discrete packets, and the act of observation is woven into the fabric of reality in ways that still unsettle people. And both of these theories have been tested to extraordinary precision. General relativity's predictions have been confirmed to something like 14 decimal places in some experiments. Quantum electrodynamics, the quantum theory of how light and matter interact, is often called the most accurate theory in all of science, with predictions matching experiments to better than 1 part in a billion. And yet they don't talk to each other. They're like two maps of the same territory drawn in completely different languages, and nobody has figured out how to translate between them. Now, people have been trying for decades, and the attempts are genuinely fascinating, even if none of them have fully succeeded yet. Let's talk about a few. Not because we're going to solve the problem tonight, nobody has, but because the attempts themselves tell you something beautiful about how physics works, about the kind of imagination it takes to push into genuinely unknown territory. The most famous attempt is probably string theory. The basic idea emerged in the late 1960s and early 1970s, and it's one of those ideas that sounds almost absurd when you first hear it, but turns out to have extraordinary mathematical depth. Here's the core thought. In the standard picture of physics, the fundamental objects are point particles, electrons, quarks, photons, things with no spatial extent, just zero-dimensional dots. String theory says, what if they're not points? What if at the very smallest scales, scales far, far smaller than anything we can currently probe, the fundamental objects are tiny, vibrating one-dimensional strings, like impossibly small loops or filaments of energy, vibrating at different frequencies. And here's the beautiful part. The different modes of vibration correspond to different particles. One vibration pattern gives you a photon, another gives you an electron, another gives you a quark. And this is the kicker. One particular vibration pattern automatically gives you a particle with exactly the properties of the graviton, the hypothetical quantum of gravity. Gravity just falls out of the mathematics, uninvited, unavoidable. When the physicist John Schwartz and his collaborators first realized this in the early 1970s, it was a genuinely stunning moment. They weren't looking for gravity. They were trying to describe the strong nuclear force, and gravity just showed up. Now, string theory comes with some baggage. For the mathematics to be consistent, it requires extra dimensions of space, Not the 3 we're used to, but 9 spatial dimensions, or 10, depending on the version. The extra dimensions would be curled up incredibly small, compactified, folded into geometries so tiny we'd never notice them in everyday life. And the number of ways those extra dimensions can be folded turns out to be enormous. Some estimates suggest something like 10 to the 500th power different possible configurations, each one corresponding to a different possible universe with different physical constants and particle masses. That's a staggeringly large number. It's led some physicists to embrace what's called the landscape, the idea that our universe is just one of an almost inconceivably vast number of possible universes, each with its own version of the laws of physics. Others find this deeply unsatisfying because it seems to undermine the hope that physics could explain why the laws are what they are, rather than just cataloging one possibility among trillions upon trillions. And here's the thing that makes string theory genuinely controversial, and it's worth being honest about. As of now, string theory has not produced a single prediction that's been tested and confirmed by experiment. Not one. It's mathematically rich. It's generated enormous insights in pure mathematics. It's led to unexpected connections between different areas of physics. There's a famous result called the ADS/CFT correspondence, discovered by Juan Maldacena in 1997, which connects a theory of gravity in a particular kind of curved spacetime to a quantum theory without gravity on the boundary of that spacetime. It's a breathtaking piece of theoretical physics, but in terms of telling us something about the actual universe that we can go out and measure, string theory hasn't delivered that yet. Some people think it will. Some people think it can't. The debate is ongoing, and it's one of the most interesting debates in all of science. Then there's the other major approach, which comes at the problem from the opposite direction. Loop quantum gravity. Where string theory starts with quantum mechanics and tries to build gravity into it, loop quantum gravity starts with general relativity, with Einstein's beautiful geometric picture of spacetime, and tries to apply quantum mechanics directly to it. The key figures here include Abhay Ashtekar, Lee Smolin, and Carlo Rovelli, working from the mid-1980s onward. And the picture that emerges is striking. In loop quantum gravity, spacetime itself is quantized. It's not smooth and continuous the way Einstein imagined. It's made of discrete, granular chunks at the very smallest scale. Space comes in tiny, indivisible volumes, like atoms of space, and area comes in discrete units too. The geometry of the universe, at the Planck scale, that's about 10 to the minus 35 meters, unimaginably small, is woven out of a network of loops, a kind of quantum foam. It's a radical idea. It means that if you could somehow zoom in far enough, the smooth fabric of spacetime that general relativity describes would dissolve into something grainy, something fundamentally discrete, the way a newspaper photograph dissolves into individual dots when you look at it with a magnifying glass. Loop quantum gravity has its own challenges. It's been difficult to show that smooth classical spacetime emerges from the theory at large scales, that the granular quantum geometry gives rise to the continuous curved spacetime we actually observe. And like string theory, it hasn't produced definitive experimental predictions, though there are some ideas about signatures that might show up in the cosmic microwave background, or in the way very high-energy photons from distant gamma-ray bursts travel across the universe. If spacetime is granular, those photons of different energies might travel at very slightly different speeds, arriving at slightly different times after a journey of billions of light years. People have looked for this. So far, the results are inconclusive. But the fact that we can even imagine testing such an idea, the quantum structure of spacetime itself, is remarkable. And there are other approaches too. Causal set theory, which imagines spacetime as a discrete set of events connected by causal relationships. Causal dynamical triangulations, which tries to build spacetime from tiny building blocks like a mosaic and studies what kinds of large-scale geometries emerge. Emergent gravity approaches that suggest gravity might not be fundamental at all, that it might arise from something deeper, the way temperature arises from the motion of atoms. Each of these is a different bet about what the universe is really like at its most fundamental level. But here's what I want you to notice, because I think it's the most important thing. Every single one of these approaches is trying to do the same thing that Newton did, that Maxwell did, that Einstein did, that Schrödinger and Heisenberg did. They're trying to find the deeper pattern, the wider room behind the curtain, the framework that contains everything we already know as a special case and extends it into the places where our current understanding breaks down. That impulse, that drive to unify, to simplify, to find the single thread that connects everything. It's the same impulse that led Thales to look at the world and say, there must be some underlying substance. It's the same impulse that led Newton to realize the force pulling an apple down is the same force holding the moon in orbit. It's the same impulse that led Maxwell to see electricity, magnetism, and light as three faces of one phenomenon. It's the same impulse that led Einstein to see space and time as one thing, and matter and energy as one thing, and gravity and geometry as one thing. And what's beautiful is that at every stage, the unification revealed something nobody expected. When Maxwell unified electricity and magnetism, he discovered light. When Einstein unified space and time, he discovered that mass and energy are interchangeable. When Dirac combined quantum mechanics with special relativity, he discovered antimatter. The existence of the positron fell right out of his equation before anyone had ever seen one. The unifications don't just tidy things up. They reveal entirely new features of reality that were hidden before, features that were always there, but that nobody could see from the narrower perspective. So if and when someone finds the theory that unifies general relativity and quantum mechanics, if someone finds that deeper framework, it almost certainly won't just be a smooth merging of the two. It will reveal something new, something we can't predict from where we stand right now, something about the nature of space or time or matter or causality that will seem obvious in hindsight, but that we simply cannot see yet. That's the pattern. That's how it's always worked. And you know, there's something deeply comforting about that, even in the uncertainty. Because it means the story isn't over. Physics isn't a finished building with the last brick about to be placed. It's a living, growing, evolving understanding, and there are still genuine mysteries, deep ones, fundamental ones, waiting to be understood. What is dark matter, the invisible substance that seems to make up about 27% of the universe's mass energy but has never been directly detected? What is dark energy, the mysterious something that's causing the expansion of the universe to accelerate? Why is there more matter than antimatter in the universe? Why do the fundamental constants have the values they do? What happened at the very first instant of the Big Bang, before our theories break down? These aren't small questions. They're some of the biggest questions human beings have ever asked. And they're open. But here's the thing I keep coming back to, and it's the thought I want to leave you with as you drift off tonight. Think about what we've covered. Think about the arc of it. We started with people looking at the world and wondering why things move, why things fall, why the stars follow the paths they do. And through centuries of careful observation, brilliant insight, spectacular mistakes, stubborn persistence, and occasional flashes of genius, we've built an understanding of the universe that is breathtaking in its scope and precision. A handful of laws, Newton's laws of motion, the conservation of energy, the laws of thermodynamics, Maxwell's equations, Einstein's field equations, the Schrödinger equation. A handful of compact, beautiful mathematical statements, and from them you can derive the motion of planets, the behavior of light, the structure of atoms, the evolution of stars, the expansion of the cosmos. The same laws that explain why a ball rolls down a hill explain why a neutron star spins 500 times a second. The same equations that describe the light from a candle describe the radiation from a quasar 10 billion light-years away. That's not obvious. That's not something that had to be true. The universe didn't have to be comprehensible. It didn't have to follow elegant mathematical laws. But it does. And the fact that a human mind, a few pounds of matter organized in a particular way on a small rocky planet orbiting an ordinary star in an ordinary galaxy, can look out at the cosmos and understand even a fraction of how it works. That's extraordinary. That might be the most extraordinary thing of all. So, as you lie here, and your thoughts start to soften, and the details start to blur together the way they do when sleep is close, the equations and the names and the dates gently dissolving into something more like a feeling than a set of facts, hold on to that feeling. The universe is knowable. Not completely, not yet, maybe not ever completely, but knowable. Piece by piece, layer by layer, each generation standing on the shoulders of the last, seeing a little further, understanding a little more. Newton's apple and Einstein's elevator and Schrödinger's equation, and the gentle hum of a gravitational wave passing through your body right now, stretching space by less than the width of a proton, carrying information about two black holes that collided 1 billion years ago. It's all connected. It's all one story, and you're part of it just by wondering about it, just by listening, just by letting your mind wander through these ideas as sleep comes to meet you. The laws of physics are still here, holding everything together, doing what they've always done, quietly, reliably, beautifully, while you rest,